Alright, this time we're going to look at calculating the concentration of aqueous ammonia necessary to precipitate iron to hydroxide. So the first thing you might have to think of it is, what is NH3 doing with FeCl2? So remember, this is going to react with water to form ammonium and hydroxide. So that's where this hydroxide is coming from. So then this would be with your chloride ion to finish that one out. So we really need to know what concentration of hydroxide, so this is kind of the net that's going on in this one. Okay, or if you want to write it from a Ksp perspective, but you should be able to go back and forth between these because it's an equilibrium. So your Ksp expression is going to be Fe plus 2 times the concentration of hydroxide squared. So I have my 4.1 times 10 to the negative 15th from the top of the page here. So that one was given. We know the concentration of the iron from the 0.0030 molar. And again, this is different from the last one because we don't have the actual volumes of these, so we're just looking for overall concentrations, and then it's the hydroxide squared that we don't know, or you could put that in for X. So your hydroxide concentration is going to be 1.2 times 10 to the negative 6th. So we have to look at this reaction here. Oops. And figure out how much of this we need to get the 1.2 times 10 to the negative 6th. So I'm just going to write a whole equation down here again just to have a little bit more room. So the Kb for this equation is 1.8 times 10 to the negative 5th. So because this is the base form of ammonia, well, ammonia is a base, I should say. If we look at this from an equilibrium perspective, we need to know what this concentration is. This is what we don't know. So initially these are going to be 0, but what we need is this concentration. So this is what our X has to be. So it's a little bit different process. Usually we're trying to find what the shift is. This is, hey, this is what we need for this one. So if I'm creating this on this side from my ice chart, I have to be losing it from this side. So this is minus 1.2 times 10 to the 6th. So that is going to be my equilibrium concentration. So then I'm just putting this into my Kb expression. Okay, remember, water's a pure liquid, so it's not going to show up in my expression. So I'm going to just go to put 1.2 times 10 to the minus 6th 2 times for both of these, and that's all going to be over X minus 1.2 times 10 to the minus 6th. So this one's just sort of a messy when you get your terms together. You're going to get these two squared, 1.2 0.44 times 10 to the negative 12th. And again, that probably is one that you should be able to do in your head. And that is going to equal, just going to cross multiply these, 1.8 times 10 to the negative 5th x minus 2.16 times 10 to the negative 11th. Get my like terms together, so I'm going to move this one over here, and then eventually I get x is 1.3 times 10 to the minus 6th molar. So that's the minimum concentration that I would need. To cause the precipitation of ammonium hydroxide. Alright, this last question is going to look at what's called selective precipitation. So we're using differences in solubility to cause the precipitation of only one ion in the solution. So this is how another mixture separation technique. So we have our two concentrations of 1.0 times 10 to the negative 4th molar copper 1 ion and 2 times 10 to the negative 3rd molar lead 2 ion. So if we're adding iodine gradually to the solution, which one is going to precipitate first? So you might look at these and say, oh, this one probably is going to precipitate first because it has the lower solubility, but remember your number of ions are not the same, so you really should do the calculation for this one before you make that guess. So I'm going to write my expressions for my two compounds. So Pb plus 2i minus, and for Cu plus 1 plus I minus. And then I'm going to substitute in what I know for my KSPs after I write my expressions here. So this one I gave you a lot of space, but we really aren't going to use all of it on this one. So for lead, I have a KSP of 1.4 times 10 to the negative 8th. I have a concentration of lead of 2.0 times 10 to the minus 3rd, and then I need the concentration of iodine squared. And then I'm going to substitute in for Cu, my 1.0 times 10 to the negative 4th. And my I minus concentration. So I'm just solving for I minus in both of those. And then for I minus on this one, it's 5.3 times 10 to the negative 8 molars. Molarity. So CuI will precipitate first, since the iodide ion concentration is lower. If the iodine concentration is kept below 2.6 times 10 to the negative 3rd, only CuI will precipitate. So any I minus concentration above that, or above the 2.6 times 10 to the negative 3rd, will precipitate both ions. So again, if you can control these concentrations, you can separate these two from each other. And that is selective precipitation.